My name is Tim Kipp, and I'm one of the partners at Oxide Games. We just incorporated ourselves in January this year, and we've been we're in the space to try and basically push the boundaries of what we can do in PC gaming and in terms of strategy gaming specifically. Dan Baker, one of the other partners at Oxide, is here with me today. He's going to talk a little bit as well. So Oxide Games is a new studio. Let's see, we've worked on a bunch of different titles. Hopefully you guys have enjoyed some of the ones that we've worked on. If you want to talk about those afterwards as well, please feel free to stick around. We're very committed to PC gaming. We feel like there's a lot of potential and a lot of performance and a lot of really interesting things that can be done in the PC space. So it's a place that we love to play and we love to work in. So why are we developing our own engine? And in a lot of cases, Nitrous is answering a lot of the problems that we've had to deal with in the past. Strategy games have some really unique demands regarding batch counts, regarding camera controls, user input, et cetera, et cetera. And they tend to be more unique to strategy games than most of the other games that you can see, especially because as a strategy game, one, we have sandbox type gameplay, and two, we really cannot control the user experience. You know, the user is the level creator. And when you have a lot of variability, it's very difficult to sort of pre-cache, pre-store, build, and reduce stuff at the same time. It tends to reduce flexibility and tends to make for a less dynamic game. The landscape has also changed, so we're now in an era where 64-bit computing, 8 cores plus is at this point common, and GPUs have gobs and gobs of power. It's beautiful. The difficulty is how do we use all this power, especially if we're transitioning from, say, older programming models. And also, and strategy games are all about, not necessarily the number of units, but there's a certain complexity that you'd expect out of a strategy game. So our next-gen rendering engine is built more like a film renderer. We're using a physically based model. Our shading is actually decoupled from rasterization, which is one of the ways that we get sort of a very clean look to a lot of the images that we're going for. So we're really trying to take a look and take a lot of cues from the film industry and try and build a renderer that gives you a really clean, crisp image. All our color values are in HDR. We have a tone mapping curve that's been basically pilfered from the movie industry, and actually we've gotten some really good results at. We're also incorporating things like bloom, motion blur, lens effects, and these are all emergent properties of the engine itself, which is really, really handy in terms of authoring time and in terms of robustness. So we've also sort of been talking about our application model. We've lovingly named it SWARM, which stands for us anyway, as Simultaneous Work and Rendering Model. This is a really fancy acronym, and what's it really about? For us, the reason why we've kind of come up with this is that as we've been talking to other partners and in talking to some of the business people we've been talking with, we needed a way of describing how it is we set up our application and how it is we work. So what it really boils down to is we've completely eliminated the functional-based threading model, and we've gone to a task-based model. And this is based on a lot of experience that we've had in the past in terms of trying to utilize all the cores on a PC. So what we've done is we've tried to design it to handle very large, very complex applications and sims. It's not just for rendering. This is also for AI. This is for physics. This is for all sorts of gameplay elements. And because of that, we tend to be incredibly scalable. So it's not uncommon for us to do 10,000 discrete tasks per frame with minimal performance implications. And we love more and more cores. So the goals, honestly, it's to push the boundaries of games. We feel like there's a lot of potential, and we want to see where that can go. It's very exciting for us to try and break new ground and try and deliver experience to people in games that they haven't been able to get at before. So we're looking at 4 cores as pretty much our standard. 8 cores is what we're planning for in the future, and we scale all the way up. I've been testing on 12 cores with pretty pleasing results, and we've got a slide or two of that later on. To do that, you've got to remove all your serial threads. So functional threading, again, is one of those models. I think Johan in his presentation sort of showed if you've got a functional threading model, you really have difficulty scaling beyond 3 cores, and that's been our experience as well. Let's see, and we also want to fully utilize the GPU. In a lot of cases, when you've got a CPU-bound game, the GPU is sitting there idle for a large portion of the frame time, and that's really unacceptable in our opinion. So bottlenecks, the GPUs are fast, obviously, especially if we can keep them fed. PCUs have many, many cores, lots of RAM, and we want to utilize all this. so we've had to look at this in terms of every aspect of the engine. You can't just focus in one particular spot. So we work heavily with the AI guys, the physics, scene management, gameplay. It all comes down to really the details. So Nitrous manages all those things so well that we can handle scenes with up to, at this point, we're getting 10,000 units at up to 60 frames a second, which is pretty entertaining. So here we have, this is a frame capture I did just the other day, and this is a frame without Mantle. So the little blue engine, I'm not quite sure how clear it is to see there, but the little blue box is Nitrous, and this is on a 4-core, 8-thread CPU. This is with 10,000 units, and this is doing 50,000 batches. And the execution time for this was well over 99 milliseconds. The GPU was basically CPU bound the entire time. And if you'll also notice, typically what I wind up doing is creating at least one worker thread per logical core. In this case, there's 6 additional driver threads, of which 3 are only active. And you can see here that there's this green block of unused time. And that's an area where it's incredibly difficult to find anything else to do. We've done all our work. We're ready to basically finish up, but we're being held back. And the reason we're being held back is because the driver and the API still require a really serial-based execution model. So what about deferred contexts? Well, we could try them, and we have tried them. You'll still see that there's lots of unusable green there as well. In addition, you'll see that now we've got 5 active driver threads, not just 3. However, the speed up has been minimal. So I've talked to a bunch of different developers. Most people say that they're getting negative gains on deferred context. We get slightly positive, but it's still not really a viable solution in our opinion. So why is it hard to optimize for the driver, right? I mean, are we just being lazy? What's going on here? And part of the difficulty is that it really is, it's a big black box, and it's very difficult to figure out what's causing overhead. In addition to that, there's a lot of trial and error. Every hardware manufacturer is going to do things slightly differently. They don't coordinate. And unfortunately, there's not really a good programming model that the API enforces. So it's hard to get predictable results, and those results may vary from version to version. In addition, the driver threads will conflict with our threads. We've seen that before. We've done a lot of work to minimize it, but still, even if they didn't conflict, the difficulty is that you don't have a very good way of actually communicating with the driver when to queue up threads. There's really no good signaling there whatsoever. So we've had to come up with a lot of different solutions to try and work around this stuff. So, I mean, obviously you guys are familiar. Minimizing state changes is super important. You can try and reduce your draw calls by moving the camera in closer. You can, call distances for various types of objects. There's lots of little tricks that we try and do. We've even been asked to back off on how many threads we use to give the driver more opportunity to execute. It's very bizarre. So anyway, for a strategy game, it is really difficult, especially in the later portions of the game, to get GPU limited. And then Dan can take over from here.
Yes. Success. You're done for the show. Yay. Well, I can try.
Yeah. No, we're fine. All right, guys. So one of the things that's kind of bothered me a little bit is everyone keeps talking about batch counts, and then it occurred to me, like, how many of you guys know what a batch is? I mean, it sounds like a cookie, like a batch of cookies. Like, what are we talking about when we say this batch? It's kind of a well-known thing in the industry, but maybe not everyone understands that terminology. And effectively, what I want to get across is a batch isn't necessarily drawing something on the screen. It could be, but it's any command we send to the GPU. It's any particular thing. And it's very analogous to a function call that we would do on the CPU. And on the CPU, for years, I mean, people are doing tens of millions, hundreds of millions, maybe even billions of function calls on the CPU. But when we think about calling and having the GPU do work, we really can't do very many at all. And this problem is so pervasive that it's kind of tilted the PC gaming industry in ways that are kind of surprising. I knew we were really having issues when I hear artists starting to talk about batch counts. That's scary to me. Because our production artists start having to do things to deal with CPU overhead in the driver, and you're like, wait, why are artists optimizing the driver? That sounds like we're in a bad situation here. And and the reason why is because it is effective. I mean, they can sometimes do things that will make the driver a little have a little less overhead, but it can be incredibly labor intensive. And the other thing is, game designers, think big. They like to think all the really cool things, and sometimes they'll ask for things that aren't necessarily impossible, but infeasible based off of kind of arbitrary constraints. I mean, I've been asked everything. How many units can you put on the screen? Could I have like 10,000? Can you have them all cast shadows? Can they have reflections? Or I was asking one of our designers the other day, do you need to zoom out on the whole map? And he's like, yeah, that'd be great. Can we see the whole map, like everything in the game at once? And I'm like, well, I don't know. And throughout the years, there's lots of suggestions. I'm sure many of you have seen lots of talks about how you can get around driver overhead and how you can get more batches down to the GPU. And there's all sorts of things, and these things make impact. And bindless textures is kind of the latest technique to bypass overhead. Geometry instancing is a popular one. However, it has a tendency to optimize the fastest type of call. So in real terms, it doesn't necessarily speed anything up. There's object packing, all sorts of things that you can try and do to decrease the number of calls. And one of the things I want to stress about this is it's kind of like asking a programmer to say, hey, can you write really big functions that are thousands of lines long, because we can't handle small functions, even though it makes your code messy and can be incredibly cost ineffective. And sometimes utterly impossible. And we really were excited about deferred context, but it really has been a failure. Like, it just didn't work. But the main point I want to say, these are just Band-Aids. Like, any one of these things by itself will give you a few percent here and there, in spite of a lot of work. So you do a lot of work and you're only getting a few percent. It's incredibly labor-intensive process. And all of this stuff really hurts the games. It's costing us a lot of money just to iterate on it. And when you're, especially early in the game design process, you're constantly reconfiguring stuff. And every time a designer wants to change something, you can be in this situation where you have to write a lot of really optimal code just to try something. If you want to stub in an asset, you have to have all this optimization just to even see if it works, and it's really not a place. And the other question I have is, I think we're missing enormous amounts of really awesome games. I think that we're so scared to try and issue a lot of draw calls and batches that we're just missing out on all sorts of things. And one of the goals of Oxide is to explore the giant space of games that haven't been made. And for us, batch performance is a crisis level situation. And the question is, why has this happened? It's not like all of a sudden we kind of woke up and said, hey, it'd be nice to do a lot of batches. But I want to show a chart here of GPU performance versus the number of batches you could actually do. And you can very easily see there's been a big disconnect in how much more powerful GPUs are getting versus how many batches you can kind of realistically do. And I've got two lines here. The red line is typical performance for an average developer. We actually do quite a bit better than average, but I thought that would be a good baseline. And the dotted line is actually what we would be doing if, according to our analysis, if we could just thread the overhead onto other cores, just claim some of that unused space. So not only are we really low, we're also a lot lower than we could be just because we're not able to use the other CPUs, are just sitting there doing nothing, and that's also really unfortunate. Which kind of brings up a point. I think what happened here is right when we started building multi-core CPUs, everything fell apart. And we didn't know it right at first, but after 3 years, it became evident. After 5 years, this gap has gotten really bad. So clearly, one of the big problems is we have not bridged this multi-CPU overhead issue or API issue. So the question is, we've spent a lot of time, way too much time, trying to figure out why there's overhead. And this isn't vendor specific. We see this across the board. There can be slight differences between vendor to vendor, but this is a generalization of what we've seen. One of the big things is that the API can often have unfortunate mismatches to the way the hardware works. And even simple things, like if you expose a feature that the hardware doesn't actually do, you end up incurring a lot of software overhead just to emulate it. And ironically, we avoid them anyway because we know that we can't use it because of driver overhead. So it's this kind of weird situation where there's a feature in the API that we can't even touch anyway because the overhead's too high. And one of the big things, and Johan mentioned it extensively in his keynote, is the lack of ability to manage GPU memory is just killing us. The overhead and and just general management problems are really hurtful. And the other second big thing is that the requirement for the driver to track with things like read after write or write after write hazards is a big problem because these are serial operations. You can't put them on other threads, and there's an enormous amount of analysis you have to do to figure it out, and that's really killing a lot of CPU. And probably the single biggest thing that we're definitely able to see, kind of analyzing the driver from our standpoint, is we can see clearly that there are serial points all over the place. We can see the threads blocking one another at the OS level. We don't know why, for every reason that do it, but we see enormous numbers of stalls and blocks between the different threads and fairly heavyweight primitives. From a mile-high view, if you didn't understand any of these kind of technical details, the real problem is that the APIs really have not evolved with what the hardware actually does. We're still using an API design that's really almost late 90s, really. I mean, it's late 90s design that we've kind of tacked more and more stuff on, but we haven't really asked the question, does this make any sense in a multi-core environment or an environment with more generalized processors? So the real question, and we've been going back and forth about this, is there a solution? When you go to a console, anyone who's done the console realizes a simple truth: there is no overhead batch problem. It just doesn't exist. And so we've kind of known for years that this shouldn't have to happen. But then we've kind of gone, well, you know, it's because they can talk to the metal and there's all these things they don't have to do. And we don't want to lose abstraction over the hardware. And so the question is, can we build something that still abstracts hardware but still can provide console-like performance? And we've been asking this for years. I mean, I have to admit, it's probably less asking. There might have been some begging involved and groveling. I was very happy when we finally heard, hey, someone's going to try this. Now is the time to do this. All of these reasons up here you can read. The GPUs have stabilized a lot. That's not the radical differences you're seeing version to version. And even if it was, the big thing, I think, is that the data itself is stabilized. It used to be that all these very proprietary floating point formats and all these odd things. The honest truth is that we've standardized. We know it's IEEE floating point. We know that we can support new normalized if we need to. We know all these things. So there's not this, you don't need to be insulated from the exact data format like we were in years past. The CPU and GPU are really able to read each other's memory types natively, and that's a big difference. The GPU is really just a general computing. I mean, calling it a GPU is almost wrong. I mean, it's not really a graphics processor unit. It's a massive parallel processing unit. It has a different paradigm as CPU, but it can do anything that you want it to do, assuming you can write the code for it. And the other kind of key thing that we're seeing is unified memory is coming. We're not going to have GPU memory and CPU memory. You're just going to have memory. And finally, the biggest thing is, like, when are we going to do this? We know we have to do this. Everybody knows we're going to have to, you know, kind of bite the bullet and create something that's got a lot less overhead. And the question is when. We were very excited when we heard about Mantle, and it's a very simple concept. Give us less. It sounds weird, but basically give us less, and we think we can do more. But there's a catch. There's a contract. There's trust now between the driver and the app. One of the reasons there's a lot of overhead is because applications can do really, really bad things. And you ever talk to a driver writer, they will give you horror stories of the things that they've seen in their lives. But we don't do the bad things. Like, we avoid them. So we're not an offender of these things. And then the real irony was we'd get in these situations where drivers trying to deal with all these hazards and these memory issues, and they don't exist in it. We've already taken care of them. In fact, all high-performance engines have taken care of all of these issues that really are going to cause the driver to be slow. So why are we doing all this work when we don't have to? A good example is state filtering, looking for redundant state. I was talking to some other people today and realized that our application filter state, the API model filter state, non-Mantle API model filter state, and then the driver also filter states. You got 3 people doing the same thing. Why is this? This doesn't remotely sound like a good idea. So the question is, what would you do for modern API? And I think the realization, the thing that makes this possible, is we don't really need that much. All a GPU is a processor that runs programs. Has inputs, has outputs. Sounds simple, right? We don't need a lot of extra stuff there. We can handle all the rest of it. We've been doing it on the CPU for decades. We can handle it on all that kind of side, on our all that management on our side. We don't want hidden CPU costs when we're making calls. We don't want threads. We don't want any of that stuff. All we really want to do is have the GPU run the programs that we're asking it to in some sort of order, and maybe some kind of more complex dependency graph. So we were excited when we got Mantle, and I think there's been a lot of speculations like this is a really difficult thing, but as I said before, we had kind of already dealt with all the things that might have made it difficult because we had to do it anyway to deal with driver overhead. So it really wasn't that difficult to get it. I don't believe it's very expensive for most modern engines to support it at all. And it was really interesting when I saw Johann's talk, and he was estimating exactly the same time we spent to port it. It took us about 2 man-months of work to support it, and that was on a pre-alpha version with very minimal sample code. I think there was a spinning cube and some, no offense to the Mantle guys, like some of the way that they set up the sample code was never how you were going to do it for an engine. So it really didn't have very much code, and some of the documentation was a little light, and the validation wasn't there, but it still only took about 2 months to get it up and working. And it really didn't affect a whole lot of minor changes to the engine. In fact, there was a lot of people that didn't realize we were supporting it. They didn't really affect them. There are a couple of small things we did, but nothing big. And one of the things I'd like to give some data about is the Mantle driver that we have, and by driver, our piece of code that interfaces into the API is only slightly bigger than the non-Mantle version. So it really isn't a very big module. The Mantle ended up being about 4,500 lines of code, and the non one was about 3,500. And that's not even fair to Mantle because I think like 500 lines of that code is just these lookup tables to figure out like what pixel format I'm supposed to be using. For us, if we can increase batch performance, it will decrease our cost. It'll be much faster to iterate, and we can do all sorts of things. We don't even know what types of games might be possible if we can get out of this trap for us. And the kind of really cool thing for us is that even though there were some really, really neat things that I've talked about for Mantle in terms of features that can give you better access to GPU, we haven't even kind of gotten to that yet. We got huge gains without even really exploiting even some of the really neat things you can do. So that was really exciting. Like we didn't even have to get to the exploitive features to get performance. They were just there automatically. So now that I actually I've kind of got a literal business hat now, I can give the business case for us. It's not Mantle's not not expensive to support. It's fairly cheap, and I think the big key is for us, it's a fixed cost. We're basically going to port our driver interface layer once, and then it's just going to work, and there's not a whole lot of extra maintenance we have to do to support it. And the big thing we're very excited about is to push the industry forward, to try out new techniques and new APIs, and boldly go where no one has gone before. But none of this would mean a whole lot for a lot of the consumers. So the question is, like, what does this benefit for a consumer? If you're a consumer, you're saying, well, I don't want this extra thing. There are certain tangible benefits. One is that you're going to get a more responsive app. That's one thing we've directly observed. We can control the queuing better. And so even when we're running at a lower frame rate than we like to be, we actually it feels faster because the overall latency is better. There's also new types of features that we can add. When you try and build a film type of renderer, one of the things we learned really fast is you need a lot more draw calls to do it. So we were able to actually add features that we weren't necessarily sure we could do for performance reasons, such as the film quality motion blur. We're attempting to do film style techniques rather than what's typically done in games. And one of the really neat things for consumers is you don't have to go out and buy the most expensive CPU to drive your best CPU. Okay, so I think the best thing to now is to actually show you Mantle in action. And let me go over what we're actually going to show here. It's going to take a little while to warm up. This is actually our internal engine demo. So we're really excited. We got the internal engine tests working on it, and we started talking to AMD saying, this is really neat. So we decided to clean it up a little bit and actually show it live. And let me iterate what this demo is going to show. We're going to show you what happens earlier, and if you saw the earlier Mantle talk, I said, well, we're going to hit 100,000 batches. So it said, well, that's cool. What happens when we get to 100,000 batches? What would that look like? And so sure enough, we turned up the engine, and we were able to do it. This isn't a pre-canned demo. In fact, it'd be impossible to show you this amount of things if each thing was hand done. Like, there's just too much content. I don't even think a full film crew could do it because there's just too many things. So what we're really doing here is showing you a game with 2 AI opponents playing each other. But one of the cool opportunities we have is we're going to publicly release this in Q1 and let everyone play with it. And the content's modifiable. I mean, people are talking about the mod community. You can add your own things to it. You can script things. Actually play around with yourselves and see what types of things could be made when you get rid of some of these constraints. So without further ado, I'll have Tim over there. Just, you don't have to switch. You just, there you go. There you go. That high tech right there. We have duct tape over the second projector. Yeah, that was some state-of-the-art stuff. And I guess I give you the demo warning that this is pre-alpha everything. So should there be an explosion or something, we expect to survive it, but there are exits there and there. I feel like we should say something snazzy right now. There it goes. Do you want to talk about it, Tim? No? Okay. Do you want just thumb up or thumb down? Oh, I've got the mic. All right. I'll give you a little background while it's loading, and then I'll let Tim chime in because I always forget stuff. So it's going to take a little while to warm up because what we're doing is we're starting a scenario for a hypothetical game. This isn't a specific game. People could ask me, when is this thing going to come out? And I'm like, well, it's actually just an engine test that we were doing, so it's not any specific game. One thing I'd like to point out is this Star Carrier actually has, how many turrets is it, Tim? It's like 50 moving turrets that are all tracking independently. And it has nothing to shoot at just yet, but every single part of that, every single turret you're seeing, including the barrels, are all tracking independently. That is a very complicated question. Because, actually, I can talk a little bit about this now. The question was how many vertices, or what's the triangle count on those? And it's a very complicated question because our render is not a, we don't render or shade triangles. We actually shade individual sample points. And we rasterize after we do that. This is much more similar to how, say, RenderMan does it. And so we shade, and one of the really cool things we can do is once we shade the object, we can actually re-render it many times to do things like motion blur. So one of the things that we're able to do is I think our virtual frame rate is like 300. I don't know, Tim set it up, but it's like 350 or 400 frames a second. I've got a couple of timers up there, and I want to just kind of show you that's the current batch count. Now, one thing to keep in mind in a modern engine is that one batch does not equal one model. Most things that get rendered have multiple passes and whole sorts of things that are happening. The time on the left is the total time between, it's actually between the fences of the GPU. So it's between when we ask the GPU, hey, are you done yet? And then submit the other things. So that's the total frame time, what you're traditionally. The submit time is actually the time that we're spending inside Mantle. And these are in milliseconds. And the final time on the right is the frame-to-frame time, which is the time we're isolating when we're not waiting for the GPU. So if we had an infinitely fast GPU, the time on the right would be our milliseconds. So right now, I don't know what the math is on 5, what is that, 200 frames a second or something? I'm not sure. So theoretically right now, we're hitting, it'll get warmed up a little bit here. If we weren't GPU bound, we would be doing something like 300 things. Now, we haven't optimized our GPU at all. We put this all together on the CPU, and Artist just checked stuff in, so we haven't even really looked at GPU performance yet. So the most fair number to look at is probably the one on the right. One thing I'd point out too is, there you can see that ship. Zoom into the carrier that's going off. There you go. That ship's going off. We're actually spawning thousands of lights in the scene too. Every single weapon impact and every single thing is actually a physical light in the scene. So we can end up in situations, which makes me grumpy sometimes when the gameplay guys put in, 10,000 lights in the scene, but we can't handle it. And so there you're seeing lots of lights being spawned. Right, I don't have anything else to say. I think, Tim, you should say something. Can we switch over to Tim before he protests?
Oh, sure, I can keep going. All right, so we want to talk a little bit more. I mean, I think it's important to point out in this demo that this isn't on, but that's okay. Can you guys hear me? You need to go up on stage. Yeah, we're part of the speaker. Yeah.
Oh, okay. Well, I'll drive then. My voice is getting dry, so I'm like running out of stuff.
I can give Dan a break here for a second. So anyway, so there's a couple other important things we wanted to make sure about this demo, because we didn't want this to just sort of be a sort of abstract graphics test, et cetera, et cetera. As Dan points out, this is an internal test that we use to test the entire engine out. So currently what we're winding up doing is each one of these spaceships on the screen is their own independent entity. They've got their own firing solution. They've got their own AI system. They're doing coordinated flocking not only within their own squadrons, but within their squadron groups itself. Each one of the shots, it's kind of funny what happens once you start giving gameplay and AI guys lots of perf to do stuff. They start doing really crazy things that you wouldn't expect. Like each one of those little bullets, the gameplay guys decided that those should all be unique and independent. And I really couldn't complain too much, because when I started profiling it, it all kind of fit through and worked. So I really didn't have too much of a leg to stand on. The other interesting thing that I think is really fun about this is that the entire thing is really dynamic and natural, which is a really important sort of test for us. So I think we're up to just around 2,000 units. Every run is a little bit different just in terms of testing, because one of the sides will always get the upper hand at some point, and we wind up winning or losing based on that. Each one of the missiles, they're independent missiles. The carrier down here that we've got up is a fantastic model that just got in. That has over 200 independent missile turrets that everyone's been lovingly trying to get to fire off. The other carrier, the one that looks more like a long green tube, has 30 different turrets, all of which have gameplay constraints, and they're putting up their own targeting solutions for all of that. Let's see, the effect system all sort of runs independently, so there's not one sort of meta object for each of those, so the trails are all independent, which means that even though we're probably only doing about 3,000 units right now, the number of supporting objects in terms of effects and things that are going off in the gameplay world is about an order of magnitude more than that. So, in reality, we've got around, let's see, if we're up to 2,000, probably around 25,000 discrete objects that we're currently working on simulating and putting together and doing everything else. You can see sort of the missiles flying up there and missiles flying below there. And I think the other thing that's kind of interesting is that, let's see, so there's LOD. All the objects have LOD. That was a really important thing. And actually, one of the things that Mantle made this much easier at is that once we start talking about techniques for reducing batch count, one of the things that you lose is sort of discrete primitives. So being able to sort of just say, sure, we'll use as many LODs as we need to, we've actually been able to start taking the artwork and optimizing it more and more. So we still have a lot of GPU optimization to go. I think we're talking about, we expect to get, well, our goal is to hit 100,000 batches. I think we can do it. Let's see, and if you look at our frame time now, even at, do I sum those two, Dan? 6 milliseconds and 2 milliseconds? Okay. So yeah, so we're at 6 milliseconds for just those 2,000 units and 20 to 30,000 batches, which has been a fantastic result for us. Well, I'll tell you what. You know what? Do we want to actually break format a little bit? I'm willing to, if anyone has any questions quickly, we could actually answer them while this is going off, and then we can finish up the rest of the slides.
What's the CPU utilization right now?
Let's see. What is the Okay, actually, you know what? That's great. I have a slide farther on down the line in Mantle for that. So I'll show you an example. There will be 2 slides further on. One is an example 4-core with 50,000 batches. Another is an example with a 6-core 12-thread machine at 80,000 batches.
How do you debug
Yeah. How do you debug 60,000 batches? There's it's really interesting. So we've been talking a lot about we're a lot more scalable than we were expecting. When we designed the engine and we put it together, there was a lot of theory, but we really had to work it out and put it together. And because of the way that we wanted it being so asynchronous, when I talked about that sort of swarm model, what really happens is that because we can do a lot of very small tasks, things go all over the place. And one of the things that we're actually doing is looking at a way of actually recording the call stacks and tying everything back together as an easier way to do it. Interestingly enough, to get that sort of really multi-threaded utilization out of what you do, you wind up doing a lot more message passing. And when you do that, you actually have a lot of context data right at the point where it breaks. So
Switch back to the slides, and let's let this run and just see what happens.
I just like letting it run, especially once we get closer to 10,000 units. It's really quite fun for us. Let's see, any other?
What hardware is it running on?
This is an FX8350 and a Hawaii board right now.
For this interaction, does it make it difficult to have multiplayer game, or just this will be restricted as a single player?
I'm trying to let me see if I can understand the question again. What was it?
So if you have all this, interaction going on,
Yes.
it's more difficult to have a multiplayer game.
Well, I suppose that depends on how you implement a multiplayer game, right? So you're right. If we were going to try and synchronize every bullet, every ship on screen, then certainly there would be huge problems there. So yes, if you wanted to do a very naive implementation of multiplayer on this, it would be very difficult to synchronize. I can't talk about that. Sorry. But I think we all know that naive is not going to work in this case. But I think we can all imagine that there are alternative methods that allow you to aggregate some of that information. What's our time like?
All right, let's go back to that.
Okay. Oh, sure.
Can you say something about, like, can you compare what kind of numbers you would have gotten if you were to do this in regular
So on regular D3D, yeah. So we've been running on both DirectX and Mantle right now. With D3D, we are getting, I am hitting a bottleneck right around 15,000 batches. I'm having difficulty breaking through that 15K barrier. Interestingly enough, when we after that, it plummets pretty dramatically. So it goes downhill very fast, and it tends to be, as far as we're able to get it out, it's all CPU bound at that point, which is really.
Can you turn me on?
Yeah.
Am I on? Oh, here we go. So we'll actually go over that in a second. This is what we were seeing before, just a review. And this actually isn't even as much stuff as we were showing. This is less stuff. And this is actually and this is an actual frame sample. We took a frame sample. I mean, yeah, you can recognize this is V2, and you actually see it. This is what we saw. We were able to identify it. And this is what we saw before Mantle. And this is after Mantle. Now, that blue section is actually the same amount of time. It's not any different. We just kind of zoomed in a little bit. And the really cool thing is that's Mantle. This is a little tiny yellow thing. It's just not big at all. And that was really exciting. And the really cool thing is we're waiting on the GPU. So we have this giant stretch of unused CPU time, but the difference is we could totally do something with that now because it's just sitting there. We're just waiting. The CPU literally could just shut down for like 15 milliseconds while it's waiting for the GPU. The other really neat thing is if you notice, there's no driver thread at all. It's gone. And that's awesome. Just to crank it up, we decided, well, what happens if we go to 12 threads? And sure enough, everything just kept scaling up. So we really don't know how many threads we can scale to, but certainly it's looking very, very promising. And we have plenty of green time of unused stuff. So this is, a lot of people ask me data, and we're trying to be, we can't be totally exact about the data right now, so we're kind of playing it safe, but we're prepared to say the following about officially about the performance numbers that we see with Mantle. The API head is reduced by at least 10x. Mantle is scaling across CPU cores much better than without it, so true performance is actually going to be a lot higher than that. And it really depends on the number of CPUs you've got. At an application level, Starstorm is 3 times faster in some cases, in many cases. It is completely changing the landscape for multi-core. In fact, it's very interesting that traditionally when you see a benchmark of a 4770K, the latest, fastest, considered the fastest desktop chip you can get, when we actually compare the 8350 to it, at least eyeballing it, I can't tell you which one's faster. I think the 83 might actually beat it. And that's just because it's a true 8-core instead of a 4-core 8 hyper-threading. And that's really interesting, the fact that we can take more cores and it just gets faster. The really kind of spooky thing is that on the 290, RX 290, which R290X, I think I messed that up, oh well, is still GPU bound. Even when I underclocked, I just decided to be crazy. I'm like, what happens if I take the machine and underclock it? Is it downclocked or underclocked? Does anyone actually do that? Are there downclock hobbyists? Is that something? Okay, well, I decided to be the first downclock hobbyist, and I said, well, let me underclock this to 2 gigahertz, and I was still GPU bound. And what does that mean? It means that the machine was still running at exactly the same frame rate, even when I clocked it, I chopped that frequency by half, and that was really neat. So this is the point of no return. I mean, the big thing for us is like we really wanted to show everybody, hey, we weren't crazy when we can do this. We're pretty sure we can do this kind of batch count. I'm pretty sure we can get rid of this problem completely. And this is on alpha hardware. We're really just barely scratching the surface of a lot of the things that we can do. We didn't spend a lot of time optimizing it, I'll be honest. I mean, how much time can I spend? We just got this stuff like a few months ago. And we're still optimizing our engine too. There's still enormous amounts of dead CPU time that we're trying to schedule and stuff. And I'm going to throw out some goals just to put even more pressure in it. I think by 2015, we should be doing 300,000 batches. And I'm going to say by 2018, we're failing if we're not doing 1 million batches at 60 frames a second. And at this point, everything starts to change. CPUs and GPUs just start calling code back and forth on each other. This hard distinction, this kind of thick pipeline is going to go away, and all sorts of interesting things are starting to happen. And right now, it seems very evident that there is a path for this. Let me give you some acknowledgements. We had to put this sample together pretty quickly. So thanks to the AMD Mantle team for their hard work and for just making it happen. A lot of people didn't believe that we could do this, and we're very happy to show that, yes, it is done. Also, big thanks to Ironclad Games and Stardock. We got a little bit of artwork from Ironclad and from Stardock, and that was extremely helpful.